Good evening, children.
Good evening, ma'am.
Good evening, ma'am.
Good evening.
Good evening, ma'am.
Good evening. I've shared my screen. Is it visible to all of you?
Yes, ma'am.
Okay. I repeat, I've shared my screen. I hope it's visible to all.
Yes, ma'am.
Yeah, good. So number systems is the first chapter in your NCERT math textbook, and we'll be getting started with this chapter. So before we take up problems to solve from this chapter, we need to have a small introduction regarding the terms we'll be using in this chapter. So what do we mean by rational numbers? So numbers of the form P by Q, where P and Q are integers. P and Q are integers, but the denominator Q should not be equal to 0. Is called a rational number. Numbers of the form P by Q, where the numerator P is an integer, the denominator P is also an integer, can be positive or negative, but the denominator should not be 0. The denominator should not be 0. It can be any integer other than 0, because 0 is also an integer. 0 is also an integer. P and Q are integers, but the denominator Q can be any integer but not 0, because we know division by 0 is not defined. Division by 0 is not defined. So the denominator Q should not be 0. It can be any integer other than 0. So numbers of the form P by Q, where P is an integer, Q is also an integer but not equal to 0, are called rational numbers. So in simple words, integer by integer is a rational number. If you find an expression of the form integer over an integer, so this condition is always there, that the denominator integer should not be 0. That condition is there. Is a rational number. So integer by integer is a rational number. And integers, we know, the collection of all natural numbers. How do you define integers? We know what integers are, but how do we define integers? The collection of all natural numbers, their negatives, including 0. The collection of all natural numbers. A collection of all natural numbers goes on like this. Their negatives of the natural numbers. The negative of 1 is -1. These are natural numbers. It goes on. So -1 is a negative of 1, -2 is a negative of 2, -3 is a negative of 3, -4 is a negative of 4, and so on. So the collection of all natural numbers, their negatives, including 0, forms the collection of integers. So this is an infinite list. This one is an infinite list. So it starts from where we don't know, -4, -3, -2, -1, 0, 1, 2, 3, 4. It goes on like this endlessly. So this is how we represent the collection of integers. So these are integers. Integer by integer is a rational number. Denominator integer should not be 0. Now a rational number is said to be in the simplest form if the numerator and the denominator have no common factors other than 1. Okay, so we're talking about the simplest form of a rational number. Simplest form of a rational number. Now, when you consider this rational number 10 by 25. Now 10 by 25 is a rational number because the numerator 10 is an integer, the denominator 25 is an integer. So integer by integer is a rational number. So the expression 10 by 25 is a rational number. A fraction is a natural number by a natural number. You've learned fraction. So rational number is integer by integer. A fraction is natural number by a natural number. So now this expression 10 by 25 is a rational number because the numerator 10 is an integer, the denominator 25 is an integer, and the denominator is not 0. So it's a rational number. Now is 10 by 25 is this rational number 10 by 25 in the simplest form? No, because the HCF of the numerator and denominator is not 1. Because the HCF of the numerator and denominator is not 1. The HCF of 10 and 25 is 5. The HCF of the numerator 10 and the denominator 25 is 5. The HCF of the numerator and denominator, should be 1. Then the rational number is said to be in the simplest form. If the HCF of the numerator and denominator, NR is numerator, DR is denominator. So if the HCF of the numerator and denominator is 1, then the rational number is said to be in the simplest form. If the HCF of the numerator and the denominator is something other than 1, it's not 1. It's something other than 1. That means the rational number is not in the simplest form. Now, when two numbers have HCF when two numbers have their HCF as 1, the numbers are said to be co-prime. The numbers are said to be co-prime. What are co-prime numbers? Two numbers are said to be co-prime if their HCF is 1. Two numbers. The two numbers need not be prime numbers. See, the term is co-prime numbers. Co-prime numbers. But the two numbers need not be prime. Any two numbers are said to be co-prime if their HCF is 1. Now you can see in this example that 10 and 25, both of them are not prime numbers. They are not prime, 10 and 25. Are they co-prime? No, they are not co-prime because their HCF is not 1. Their HCF is not 1. The HCF of 10 and 25, it's not 1, it's 5. So 10 and 25 are not co-prime numbers. So coming back to the simplest form of a rational number, now 10 by 25, the HCF of 10 and 25 is 5, which means you can simplify this further. So 5 2s are 5 5s are. Now 2 by 5. See, 2 by 5 is an equivalent fraction of 10 by 25. 10 by 25 and 2 by 5, they are equivalent fractions or equivalent rational numbers. They are equivalent rational numbers. 10 by 25 is the same as 2 by 5. 10 by 25 is the same as 2 by 5. Now look at 2 by 5. What is the HCF of the numerator 2 and the denominator 5? It's 1. That means 2 by 5, the rational number 2 by 5 is in its simplest form because it cannot be simplified any further. And that's because the HCF of the numerator and denominator is 1. Now consider 15 over 23. You can even take this minus 15. So minus 15 is an integer. 23 is an integer. Integer by integer is a rational number. The HCF, you can ignore the negative sign. Just take the numbers 15 and 23. The HCF of 15 and 23 is 1. The HCF of 15 and 23 is 1, wherein 23 is a prime number, whereas 15 is not a prime number. 15 is not a prime number. 23 is a prime number. The HCF of these two numbers is 1, which means the rational number minus 15 by 23 is in its simplest form. Now, since the HCF of 15 and 23 is 1, 15 and 23 are co-prime numbers because their HCF is 1. 15 and 23, they are co-prime numbers because their HCF is 1. Two numbers, they need not be prime numbers. Two numbers are said to be co-prime if their HCF is 1. Okay. So that's about rational numbers. Integer by integer is a rational number. The denominator integer should not be 0. Simplest form of a rational number, the rational number, the numerator and the denominator, the HCF of the numerator and the denominator should be 1. If the HCF of the numerator and denominator is 1, then the rational number is said to be in the simplest form. Now, when the HCF of two numbers is 1, then the two numbers are said to be co-prime. If the HCF of two numbers is 1, then the two numbers are said to be co-prime. So integers, so we say integer by integer is a rational number. What are integers? The collection of all natural numbers, their negatives, including 0, form the collection of integers. So a rational number is integer over an integer, right? So say 13 by 21 is a rational number because 13 is an integer, 21 is an integer. Integer by integer is a rational number. Now, 1 by, or say 11 by 25, rational number. Now, there is a difference between these two rational numbers in terms of their decimal expansion. There is a difference between these two rational numbers in terms of their decimal expansion. Now, when you divide, all of you use the calculator, you can, I'll give you some assignment wherein you can divide and find the decimal expansion of a few rational numbers. For now, you can just use a calculator. Tell me the value of 11 by 25. 11 by 25. I have a calculator beside me.
0.44, ma'am.
11 by 25. Yeah, quickly. 0.44. All right. Now, next 13 by 21. The decimal expansion of 13 by 21. 0.619. 0476. Okay, I'm not writing the 6 again. 619047. Yeah. Yeah, I was telling you that both 11 by 25 and 13 by 21 are rational numbers, but there is a difference. There is a difference in their decimal expansions. Now, how will you find the decimal expansion? By performing the long division. So when you divide 11 by 25, remember that the numerator is the dividend. Don't put the bigger number. You don't take the bigger number as the dividend and the smaller number as the divisor. It's not like that. The numerator is always the dividend and the denominator is the divisor. Okay, so 11 is a dividend, 25 is the divisor. So when you perform the long division, the quotient is 0.44 and the remainder will be 0. The remainder will be 0. Now, when you divide 13 by 21, 13 is the dividend, the numerator is the dividend, the denominator is the divisor, right? So when you perform the long division, so you get 0.619047. So division goes on. You know, you will not get, see, when does the division come to an end? When do you stop the division process? When you get 0 as the remainder. You stop the division process, or you understand that the division has come to an end when you get the remainder as 0. But what if you don't get remainder 0? That means the division is going on and on. So you feel it will come to an end at a particular point, but no, it goes on and on and on and on. So you're forced to stop at a point, right? You're forced to stop. So this is what can happen when you perform the long division. Either the division can come to an end with a 0 remainder, or the division can go endlessly. And you realize that it's going on endlessly because you know you're not going to get 0 remainder. Now, how do you know that you will not get? What if you get 0 remainder in the next step and you didn't perform that? So how do you know? So that I'll just show you some division processes, which I have it in the slides behind. For now, I'll just tell you here. So when the division will not come to an end with a 0 remainder, you will see that the remainders start repeating themselves. Like say, you will get a particular remainder, like say 2. You keep getting the remainder 2 at every stage. Or a set of remainders will repeat themselves. Say like you get remainder 2, then you get 4, 5, 1. Again, you get remainder 2, 4, 5, 1. Again, you get the remainder 4, 2, 4, 5, 1. So when remainders start repeating, you will see that in the quotient, the digits in the quotient also will start repeating. So if you have 4 repeating remainders, in the quotient also you will see that 4 digits are repeating themselves. So you will realize that the division is not going to come to an end with a 0 remainder when a remainder repeats itself. For example, the remainder 3, you keep getting the remainder 3. Every time you divide, you get the same remainder 3, 3, 3, 3. Every stage you get the same remainder 3. Or either a remainder repeats itself or a set of remainders. Set of remainders can be 2, 3, 4, 5, 6, 7, any number. Any number. So either one remainder, the same number repeats itself, or a set of remainders. As I told you, it can be 2, 3, 4, any number of remainders. A set of remainders keep repeating themselves. So you subtract, you get remainder 2. Then again, you continue the division. Next stage, you get the remainder 4. Then you continue. Next stage, you get remainder 5. Then you get 1. Again, you get the remainder 2, 4, 5, 1. Again, the same set repeats 2, 4, 5, 1, 2, 4, 5, 1, 2, 4, 5, 1. And you will see that in the quotient also, a set of 4 digits, not the same numbers 2, 4, 5, 1. Some other 4 digits will repeat themselves. So when remainders repeat, that means the division is not going to come to an end with a 0 remainder. So when you perform the long division, 2 things can happen. Either the division will come to an end, or the division can come to an end with a 0 remainder, or the division will never come to an end with a 0 remainder. The division will go on, and that you realize when a remainder repeats itself or a set of remainders repeat themselves. So that's what will happen. So now I'll just clear the screen right again. So 11 by 25. When you divide 11 by 25, 0.44. That means that the division comes to an end with a 0 remainder. And you can see that the quotient is a terminating decimal. The quotient is a terminating decimal. Terminating meaning, as a word says, it stops, terminates, it ends. The the quotient 0.44. It has finite number of digits. You can count 0.44. That's all. Terminating decimal. Because the division has come to an end with a zero remainder. 11 by 25 is a rational number because the numerator 11 is an integer. The denominator 25 is also an integer. Now the rational number 11 by 21 is in the simplest form because the HCF of the numerator 11 and the denominator 25 is 1. The HCF of the numerator and denominator is 1. That means the rational number is in the simplest form. You cannot simplify it any further. When you perform the long division, when you divide 11 by 25, the division comes to an end with a zero remainder and the quotient is 0.44, which is a terminating decimal or which is called a terminating decimal. Terminating because it has a finite number of digits, 0.44. That's it. It ends there. But in the other example we took, I don't remember what I wrote. What did I write? Something, but I wrote 15 by 23. Okay, I don't remember.
13 by 21.
21
13
I
by
wrote.
21.
No.
13 by
21.
21.
Come again? What?
13 by
21.
21. Yeah.
Okay. It's okay. Okay. Oh, yeah, right. Okay, so we get 0.619047. Yeah. So when you divide 13 by 21, you see that 1, 2, 3, 4, 5, 6. 6 different remainders will repeat themselves. And that's why in the quotient you have these 6 digits repeating themselves. The quotient will look like the 0.619047. Again, 619047. Again, 619047 goes on endlessly. And you will see that 6 different remainders will repeat themselves. 619047, 619047 will happen on and on, go on and on. The division will not come to an end with a zero remainder. So how do you write that? 0.619047, the same set of digits repeat in the quotient. So you don't write it again. Just write the set once and place a bar on top of it. Place a bar on top of it, which indicates that the same set of digits repeat themselves. You can also write it like this, 0.619047. You can repeat the set once, 619047, and use dots like this. To use the dots, you need to write that set at least one more time. Only then you give an indication that that particular set is repeating. You should not do this. You cannot write 619047 and simply put dots like this. This is very vague because you're not clear as to which digit or which set of digits are repeating. Is 7 alone repeating, or is 47 repeating, or is 047 repeating? Right? So it should be clear. These two are not the same. They're not the same. These two are not the same. These two are the same. What you see here and here, these two are the same. This one and this one. 0.619047 and a bar on top of it is the same as 0.619047. Once again, 619047 and use the dots to say that the quotient goes on and on like this. So you must repeat that set at least once and then use the dots. So now this decimal is called a non-terminating. Why non-terminating? Because it doesn't end. So non-terminating. But it's repeating, right? A set of digits are repeating themselves. So we call this decimal a non-terminating repeating decimal. Non-terminating because the digits go on and on in the quotient, and also in the division process, the division will keep happening with a set of remainders repeating themselves. So since the division will go on and on with a set of remainders repeating themselves, In the quotient also, a set of digits will keep repeating. So this decimal, this quotient is called a non-terminating because it doesn't terminate, but repeating decimal or recurring decimal, recurring or repeating. So the quotient here is called a non-terminating recurring decimal or repeating decimal. Now, only these two things can happen when you divide an integer by another integer. That is, when you find the decimal expansion of a rational number. When you find the decimal expansion of a rational number is integer by integer. So when you perform the long division, only two things can happen. Division comes to an end with a zero remainder. In this case, the quotient is a terminating decimal. The other cases, the division does not come to an end because we find that a remainder or a set of remainders keep repeating themselves. So the division does not come to an end. And when you look at the quotient, the decimal obtained there is non-terminating, but repeating, as we understood, because a digit or a set of digits will keep happening, will repeat themselves. So in the second case, the division does not come to an end. Then the quotient is a non-terminating, repeating decimal. So when you divide an integer by an integer, or when you find the decimal expansion of a rational number, you can only get these two results. Either the result is a terminating decimal or a non-terminating but repeating decimal only. So there is another decimal form. There is another decimal form which is called a non-terminating, a non-repeating or non-recurring decimal. Non-terminating, non-recurring, non-repeating decimal. Now that cannot happen when you find the value of a rational number. You will not get such a decimal as the value of a rational number. So these are the three types of decimals: terminating decimal, non-terminating, repeating or recurring decimal, non-terminating, non-repeating, repeating. The other term for repeating is recurring decimal. Now the first two have or can be represented as a rational number. Terminating decimals and non-terminating repeating decimals are rational numbers because they have an equivalent p by q form. Now this, if it's a terminating decimal, it will have a p by q form. It will have an integer by integer form because such a decimal is a result of a division process. How did we get this terminating decimal? How did we get this terminating decimal? It's a result of a division process. Of a division process where the division had come to an end with a zero remainder. How do we get this non-terminating repeating decimal? It's the result of a division process where the division did not come to an end. The division went on, and that's when we got the quotient as a non-terminating repeating or recurring decimal. So this one also has a p by q form. Because these two are a result of division process. Division means what? Integer by integer, no? You divide one number by another number. You divide an integer by another integer. So rational number. So these are from rational numbers. Now, what about non-terminating, non-repeating or non-recurring decimals? Now, when you divide an integer by an integer, you cannot get such a decimal expansion. The quotient cannot be, the quotient can be non-terminating, but it will be repeating. When you find the value of a rational number, the quotient can be non-terminating, but it will be repeating. So how will this happen? When will you get a non-terminating, non-repeating or non-recurring decimal? Now this one is not a result of a division process. When you divide a number, when you divide an integer by another integer, you cannot get such a decimal, value. Now these are from square roots of imperfect squares. Now square root, supposing you try to find the square root of 5. Okay, square root of 5. I'm using the calculator. So square root of 5 is 2.2360679774997 goes on. Now, how do we understand that this decimal expansion? It's non-terminating because it goes on. But how do we understand that it is non-repeating? Because you can see here in this particular decimal expansion, you can see the digit 6 here, which repeats here. But here after 6, you have 0. But here after 6, you have 7. Now, okay. So now see a 7, 9. Then again it is 7, 7. You don't find. Now my calculator shows, I think, 12 digits or 15 digits. You can count here 1, 2, 3, 4, 5, whatever. All right. So you take a bigger calculator which can display more number of digits. You will see that you will not find a pattern. You will not see that a digit or a set of digits are repeating themselves. The decimal part will be very vague. You cannot find a digit or a set of digits repeating themselves, which is why, but then the decimal value will keep going on and on. It doesn't end. That's why non-terminating and non-repeating, because no digit or a set of digits repeat themselves in the decimal portion. This is the decimal portion. This is the integral part. Before the decimal point is called the integral part. This is the decimal point. What you see before the decimal point is called the integral part. Integral part. And this one is the decimal part. Decimal part. So in the decimal part, you will not find a digit or a set of digits repeating themselves, and hence non-repeating or non-recurring. And it's non-terminating because it goes on and on. So non-terminating, non-repeating or non-recurring decimals are the results from the square root of an imperfect square, because square root of 100 is 10, because 100 is a perfect square and square root of 100 is 10 and 10 is 10 by 1. Integer by integer, it's a rational number. Square root of 100 is a rational number. If you're asked to decide, is this rational or irrational? Square root of 100, is it rational or irrational? It is rational. See, always find the value. We should not just go by this square root symbol. Just because it is square root of something doesn't mean it's irrational. Okay, so square root of 100 is 10 and 10 is 10 by 1. Integer, 10 is an integer, 1 is an integer. Integer by integer is a rational number. So square root of 100 is a rational number. Because the value of square root of, I said square root of 10, no? Sorry, square root of 100. Square root of 100, I'm sorry. So square root of 100, the value of this one is 10, which is 10 by 1, integer by integer, rational number. So these two decimal expansions are from rational numbers. The second one, the third one is from an irrational number. What is an irrational number? An irrational number does not have a p by q form. Numbers that cannot be expressed in the p by q form. Numbers that do not have a p by q form, where p and q are integers, q not equal to 0, are called irrational numbers. Rational numbers have a p by q form, integer by integer form. Irrational numbers, okay, irrational numbers do not have a p by q form. That's all. Rational numbers have a p by q form. Irrational numbers do not have a p by q form. What is this p by q form? Integer by integer form. Irrational numbers don't have an integer by integer form. Then how do they look like? So like this. So square root of 5. Now square root of 5, you can say that square root of 5 is square root of 5 by 1. But this one is not an integer. See, simply because we write something by something is not a rational number. Something by something is not a rational number. Now root 2 by root 3 is not a rational number. Just because it is something over something, it doesn't become a rational number. It should be integer by integer. Now this one is not an integer. How do we know it's not an integer? Because integers are natural numbers. Integers are natural numbers. Their negatives goes on, okay, including 0. These are integers. Only this collection forms integers. So square root of 2, do you find it here square root of 2 in this collection? Will you find square root of 2 here? No. So this one is not an integer. Similarly, this one is also not an integer. It's not an integer. So this one may look like something by something, but since it's not integer by integer, it's not a rational number. So this one is an irrational number because it does not have a p by q form. Don't get confused. So when we say p by q form, it is integer by integer form, not something by something. Anything by anything cannot become a rational number. Only integer by integer is a rational number. So root 2 by root 3, this expression, it's not a rational number. It is an irrational number. So that's about rational and irrational numbers. Numbers that have a p by q form, rational numbers that do not have a p by q form, that is integer by integer form, are irrational numbers. Rational numbers have two types of decimal expansions: terminating decimal expansion or non-terminating repeating decimal expansion. Irrational numbers have a non-terminating, non-repeating decimal expansion. Irrational numbers have a non-terminating, non-repeating decimal expansion. And from where do we get terminating and non-terminating repeating decimals? When we perform the division process, the long division process. The quotient can be a terminating decimal or a non-terminating repeating decimal. But non-terminating, non-repeating decimals are not results of the long division process. So they are the values of the square root of an imperfect square, the cube root of an imperfect cube. Now say cube root of 30. 30 is not a perfect cube. So the cube root of 30 is an irrational number because its decimal value is non-terminating, non-repeating. 3 point something it will be. Cube root of 30 is 3 point something. And 3 point, the decimal part will have so many digits, but you will not find a digit or a set of digits repeating themselves. But the decimal value will go endlessly, so non-terminating, but nothing is repeating. So non-terminating, non-repeating decimal. 30 is I repeat, 30 is not a perfect cube. So the cube root of 30 is an irrational number. That is, the value of cube root of 30 will be an irrational number. The value will be 3 point something. This decimal part will go on and on, so non-terminating. And it will be non-repeating. No digit or a set of digits will repeat themselves. So irrational numbers will have a non-terminating, non-repeating decimal expansion, and they are the values of square roots of imperfect squares, cube roots of imperfect cubes, and so on. Now this pi, you've come across this, right? area of a circle is pi r square. Pi is the ratio of the circumference to the diameter of a circle. Pi is the ratio of the circumference to the diameter of a circle. And for calculation purpose, we take pi as 22/7. For calculation purpose, when we find the area of a circle, pi r square, so we say 22/7 into whatever is the radius, so 10 into 10. For calculation purpose, we take pi as 22/7. Now 22/7 is a rational number because 22 is an integer, 7 is also an integer. Integer by integer is a rational number. So 22/7 is a rational number because it's integer by integer. But pi is not a rational number. The value of pi is a non-terminating, non-repeating decimal. The value of pi, the real value of pi, the actual value of pi is a non-terminating, non-repeating decimal, which makes pi an irrational number. Why is pi irrational? Because the value of pi is a non-terminating, non-repeating decimal. So pi is irrational. But while using pi in a formula, for calculation purpose, we take pi as 22/7. So not to mistake, pi is not exactly equal to 22/7. Just for calculation purpose, to enable us to solve, we just take pi as 22/7. Actually, it is 3.14 and goes on like that. So millions and millions of decimal places mathematicians have computed. So when you're asked this question, is 22/7 rational? Without any doubt, say yes, because it's integer by integer. So it is rational. But pi, the value of pi is a non-terminating, non-repeating decimal, which makes pi an irrational number. So pi is not exactly equal to 22/7. Okay. Now, rational numbers and irrational numbers. And irrational numbers together are called real numbers. Real numbers. Rational numbers and irrational numbers together. The collection of all rational numbers and irrational numbers form the collection of real numbers. So a rational number is a real number. An irrational number is a real number. Like a tiger is an animal. A lion is also an animal. But every animal need not be a tiger. So every real number is not rational. Real numbers can be rational or irrational. Real numbers can be rational or irrational. So if you're asked, or if you're given the statement and asked to say if the statement is true or false, every real number is rational. Every real number is rational. No, real numbers can be rational or irrational. So every real number is rational? No, false. Or every real number is irrational? False. But the converse, the other way, every rational number is a real number. True. Every rational number is a real number. Every irrational number is also a real number. So be careful. Certain things we do understand, but might get confused while answering true or false. So just take care. Understand that rational numbers plus irrational numbers, both together are called real numbers. So a rational number is a real number. Irrational number is a real number. But every real number is not rational because there is irrational also, right? So be careful while answering true or false for such statements. Now tell me if this is true or false. Every integer is a whole number. Every integer is a whole number. True or false? Every integer is a whole number.
False.
False. Correct. Because every integer need not be a whole number. Now -5 is an integer, but it's not a whole number. But yes, 7 is an integer and it's also a whole number. 7 is an integer, it's also a whole number. Okay, for this it's true, but it's not always true. When you say a statement is true, it should be always true. Even if there is one exception, it is false. Even if there is one exception, it is false. A statement is said to be true only if it is always true. There should not be any exception. Even if there is one exception, the statement is false. An example for that is every natural number is a whole number. True or false? Every natural number is a whole number.
No, ma'am. True, ma'am.
Every natural number is a whole number.
False. True, ma'am.
False, ma'am.
I want one answer because now this is too simple to understand. Please think again, and all of you, I want all of you to give the same correct answer.
I think it's true.
It's true, ma'am.
True, ma'am.
True, ma'am.
Yeah. So ask yourself 1, 2, 3, 4, 5, 6. It goes on like this. Every natural number. Is this one a whole number? Yes. Is this one a whole number? Yes. Is this one a whole number? Yes. Every natural number is a whole number. Now the converse. Every whole number is a natural number. Is this true?
No, ma'am. It's false.
Yes, ma'am.
It's false. It's false because of only this exception. Only because of this exception. Because 0 is a whole number and it's not a natural number. Except for 0, it is true. Every whole number is a natural number. What are whole numbers? 0, 1, 2, 3, this collection. This collection. Every whole number is a natural number. Yes, all of these are natural numbers, except this one. This one is a whole number, but it's not a natural number. This is the only exception. Otherwise, it's true. No, there is an exception, no? So it's false. Because it's not always true. So every whole number is a natural number. 0 is a whole number, but it is not a natural number. It's not a counting number, no? Natural numbers are counting numbers. When there are some objects lying on a table, how do you count them? Like say some geometrical shapes like this. So how do you start counting? We don't count 0, 1, 2, 3, or we don't say -4, -3, -2, -1. How do we start counting? We say 1, 2, we count from 1 and say 2, 3, 4. So how many shapes are here? We say 1, 2, 3, 4 shapes. So counting numbers are called natural numbers. Counting numbers, including 0, are called whole numbers. Okay. So 0 is a whole number, but it is not a natural number. So the statement is false. Okay, so rational number, simplest form of a rational number. And I also told you what is meant by co-prime numbers. Two numbers They need not be prime. Two numbers are said to be co-prime if their HCF is 1. And also a rational number is said to be in its simplest form if the numerator and denominator are co-prime. If the numerator and denominator of the rational number, they are co-prime, that means their HCF is 1. That means the rational number is in the simplest form. And a rational number can be expressed as a terminating decimal or a non-terminating but repeating decimal. Irrational numbers do not have a P by Q form. And they are non-terminating, non-repeating decimals, which are the values of square roots of imperfect squares, cube roots of imperfect cubes, the value of pi, and so on. Just write it in short. Rational numbers, terminating decimal expansion, non-terminating repeating decimal expansion. Irrational numbers, this one has a P by Q form. This one does not have a P by Q form. And the decimal expansion is non-terminating, non-repeating decimal. Non-terminating, non-repeating or non-recurring decimal. Terminating decimal, non-terminating, repeating decimal. Both these are rational numbers. They have a P by Q form. This one is not this decimal value, this decimal expansion is not a result of this division process. Okay, so it's not from a P by Q. It's not by dividing P by Q. And rational numbers and irrational numbers together are called real numbers. And on the number line, every real number can be represented on the number line. Every real number has a unique position on the number line. Every real number has a unique position, its own position on the number line. That's why the number line is called the real number line. Number line is called the real number line because every real number has a unique position, its own position on the number line. You can represent every rational number, every irrational number on the number line. Every rational number and irrational number have their own unique position on the number line. That's why, so rational, irrational together, they are real numbers, right? That's why the number line is called a real number line. And very important, between two real numbers, there are infinitely many real numbers. Between two real numbers meaning they can be rational or irrational. So between two real numbers, that is between say two rational numbers, or say between two irrational numbers, or say between a rational number and an irrational number. Between two real numbers. So it can be between two rational numbers or between two irrational numbers or between a rational number and an irrational number. Between any of these, there lie infinitely many rationals and irrationals. When you take two rational numbers, between them, there are infinitely many rational numbers as well as irrational numbers lying. When you take two irrational numbers, between two irrational numbers, there are infinitely many rationals and infinitely many irrationals. Again, between a rational number, if you take a rational number and another irrational number, between these two between this rational number and irrational number, there are many, infinitely many rationals and irrationals lying. So between two rational numbers, there are many rationals. Between two rational numbers, there are many irrationals also. Between two irrational numbers, there are many rationals, many irrationals. Between a rational and irrational number also, there are many rationals, many irrationals. That's why we say between two real numbers. Between two real numbers, between one real number and another real number. So real means it can be rational or irrational. It can be rational or irrational. Between two real numbers, there are infinitely many real numbers. That means it can be rational or irrational. Between two real numbers, there lies infinitely many real numbers. So between two rationals, there are many rationals and many irrationals. Between two irrational numbers, there are many rationals, there are many irrationals. Between a rational number and an irrational number also, there are many rationals, many irrationals. Class, use emoji, raise your hand. Sai Smriti, Surya, Harsha. Priya, Yarni, Aishwarya, Gayatri. What about Lakshana and Netra? Are you there? Netra, Lakshana? Okay. Yeah. So now, tell me if one second. Now, is this a terminating decimal, a non-terminating repeating decimal, or a non-terminating non-repeating decimal?
Non-terminating.
Terminating.
Non-terminating repeating decimal.
Okay. Okay, non-terminating repeating decimal. Okay, then somebody said repeat. Somebody said I got a different answer.
No, terminating and repeating.
No, there's nothing like that. Terminating is just terminating. Only in non-terminating we have non-terminating repeating. Who's that?
Non-terminating, ma'am.
Non-terminating. Terminating. How many of you say terminating?
Sai Smriti, ma'am.
Sai Smriti and I think Gayatri, right?
Yes, ma'am.
Okay. All right. Okay. Now, when we observe this decimal expansion, you see that it comes to an end here. You don't find 1 more 2 1 4 after this. It ends there because you don't see the dots. Because you don't see the dots after this. So this one is clearly a terminating decimal. This one is a terminating decimal because it stops here. That's all. 1, 2, 3, 4, 5. Okay, so 3, 6, 9, 12, 15, 18, 21. After the decimal point, there are 21 digits. That's all. It ends there. So terminating decimal. See, 181.214 can repeat itself 500 times also, but it ends there, no? So terminating decimal. The decimal part can be very lengthy also, but if it ends at a point, it's terminating. See, we say terminating, non-terminating by looking at the decimal part, not the integral part. The integral part does not decide what kind of, decimal it is. The integral part does not decide. The decimal part decides. So if the decimal part ends, it can end very far also, but it ends. After the decimal point, say there are some 1 lakh digits. Okay, so it ends there, right? It's a terminating decimal. Now, when we write this as 181, so 181.214 and dots like this, or 181.214 and a bar like this. These two, they're the same. Both are the same. 181.214, 214 dots like this, or 181.214 and a bar on top of 214. Both represent the same. Now, this one is a non-terminating because it's not coming to an end. See, it's going on, no? The dots or the bar says that the decimal part goes on and on. So non-terminating. The dots here or the bar here suggests that the decimal part is not coming to an end. It's going on and on. That's why non-terminating. Repeating because these three digits, 214, they repeat themselves. 214, 214, 214, 214 endlessly. That's why non-terminating, repeating. While this one is not non-terminating, it is terminating. It stops here. That's it. So this one is terminating. The first one is terminating. This one is terminating. While this one is non-terminating but repeating. So 181.214, 214, 214, 214 is not equal to 181.214 recurring. They're not the same. Here 214, 214, 214, 214, 4 times. That's all. It ends there. Terminating decimal. Whereas here 181.214 and a bar on it says it goes on and on. So these two are not the same. This one is terminating decimal. This one non-terminating repeating decimal. But if we place dots here, yeah, then both are the same. Then both are the same. Now, so how do we recognize non-terminating, non-repeating decimals? So the decimal part goes on endlessly. The decimal part goes on like this. So when no digit or a set of digits repeat themselves, the decimal part is vague. You don't find any pattern in the decimal part. You don't find a pattern in the decimal part. So this one is non-terminating because we see the dots. So non-terminating. Because of these dots only we say non-terminating. And non-repeating because there's no pattern. There is no pattern. So non-repeating. See, if we write 5703.1810097311311987 and stop like this. This one is a terminating decimal because it ends here. That's all. 87987. That's it. Terminating decimal. But if these dots are placed after the digits in the decimal part, these dots suggest that they are the decimal is non-terminating and non-repeating because there is no pattern in the decimal portion. This one is terminating decimal. This one non-terminating, non-repeating decimal. Yeah. Is this a rational number or an irrational number? This one is an expression. Cube root of 9 by 72 is an expression. You will have to comment if this expression represents a rational number or an irrational number.
Irrational.
Same,
Irrational number.
ma'am.
Irrational number.
See, every number, every number that exists can be classified as rational or irrational. Every number that exists can be classified as rational or irrational, like living things, non-living things. Something that's not a living thing is a non-living thing. In the same way, numbers are either rational or irrational. Real numbers. Real numbers, our study is only about real numbers. There are numbers which are called imaginary numbers or complex numbers. Oh, we're not studying them. We're not talking about that at all. We're not talking about imaginary numbers, complex numbers. No. Our study is restricted to real numbers. That is numbers that exist. So when we say numbers, we are talking only about real numbers. So every number can be classified as rational or irrational. Every number you see can be classified as rational or irrational. Yeah. So now this is a number. This is an expression. It represents a number. Now, is it rational or irrational? Yeah. Again, rational or irrational?
Irrational number.
Irrational. Raise your hands. Lower your hands and raise your hand again. If you say it's irrational, I just want to know if all of you agree on that. Surya does not agree? Okay. Okay. So this one is an irrational number. Why irrational? Because we can see the cube root symbol. Cube root. But let's see if we are right. Now, before we comment if a number is rational or irrational, you need to simplify the number. You need to find the real value of the number. It looks like this. It looks like this. Now, supposing your teacher has given you, if she says your score is like, say this one. This is what you scored in your exam or test. So what is the value of this one? 8. So you have scored 8, maybe for 10. What is the value of this? Can we understand this further? Okay. 9 ones are 9, 9 8s are 72. So we have cube root of 1 by 8. Now the cube root of 1 by 8 is cube root of 1 by cube root of 8. Cube root of 1 is 1, 8 is 2. And if you can recall from last year, cube root can be positive or negative. All right, so here it is 1 by 2. The cube root of 1 is 1. The cube root of 8 is 2. No, I meant cube root of -8, no, is -2. Cube root can be negative or positive. Cube root of -8 is -2 because -2 into -2 into -2 is -8. So cube root of 1 is 1, cube root of 8 is 2. So the value of cube root of 9/72 is 1/2. 1 is an integer. 2 is also an integer. Integer by integer is a rational number. So before we decide or comment if the given number is rational or irrational, we need to simplify. Not always you can simplify, but you will have to try to simplify. If possible, simplify and then comment. Now, supposing it was cube root of, say, 10/11. Now, this one cannot be simplified further. You cannot do any further simplification with this one, cube root of 10/11. Nothing can be done. Yeah, then straight away you can give your answer. It is irrational. It's irrational. Cube root of 10/11 is irrational. But supposing you have cube root of -64. Cube root of -64 is -4 because -4 into -4 into -4. Minus multiplied with itself 3 times is minus. 4 4s are 16, 16 4s are 64. So the cube root of -64 is -4. So cube root of -64 is -4, which is -4/1, which is integer by integer. -4 is an integer, 1 is an integer. Integer by integer is a rational number. So this one is a rational number. This is rational. Just because you see it with the square root symbol or the cube root symbol or the 4th root or the 5th root or the whatever root, it doesn't mean that it is irrational. It's not like that. So if you can find its value, find its value. If you can simplify, simplify. And then comment if it is rational or irrational. So this one is an irrational number. This one is irrational. While this one is rational because its value is -4, which is -4/1, integer by integer, rational number. This one also on simplifying, we get 1/2. First we simplify 9/72. 9 1s are 9, 9 8s are 72. So we have cube root of 1/8. And the cube root of the numerator 1 is 1. The cube root of the denominator 8 is 2. 1/2. Integer by integer, rational number. So this one is a rational number. With this knowledge, help me answer these questions. Yeah, children. Now, the heading is classify as rational or irrational. If it is a terminating decimal, say it is a rational number. If it is a non-terminating repeating decimal, say it is a rational number. If it is a non-terminating, non-repeating decimal, then say it is an irrational number. That's all. That's how you decide. You first tell me if it is terminating, non-terminating, and then you tell me if it is rational or irrational. So the first one, 20.3232. Is it a terminating decimal? It's a terminating decimal. If it is a terminating decimal, is it a rational number or irrational number?
Rational number.
Rational number. Second one, that is B. Is it terminating or non-terminating?
Non-terminating.
Is it repeating or non-repeating?
Repeating.
Repeating. It's non-terminating, repeating. Then is it rational or irrational?
Rational number.
Rational. Terminating and non-terminating, repeating. These two are rational numbers. Non-terminating, non-repeating, irrational number. Yeah. C. Is it terminating or non-terminating?
Non-terminating.
Non-terminating.
Non-terminating. Now look at the decimal part. Do you find a digit or a set of digits repeating themselves?
No, ma'am.
Yes.
Two 2939, 2939,
Yes, ma'am.
2939, again 2939. It's repeating, no? The dots say that it is non-terminating. But when you look at the decimal part, we see the digits 2939, again 2939. Repeating, non-terminating, repeating decimal. So it is
Rational number.
rational number. Yeah, D.
Rational number. Terminating.
Terminating.
Not
How is it? How is it terminating?
D is
0.09. A bar on 09 means 0.0909090909 going on endlessly. This is what is written as 0.09 recurring. 0.09 and a bar on top of this is nothing but 0.09090909 happening endlessly. So this one is a non-terminating but repeating decimal. So rational or irrational?
Rational.
Rational. What E? What's the cube root
Rational
of?
number.
Yeah, what's the cube root of 729?
9.
9.
9.
9.
9.
9 into 9, 81. 9 into 9, 81 into 9, 729. So the cube root of 729 is 9. Is 9. And 9 is 9 by 1, which is integer by integer. So it's a rational number. What's the fifth root of 32?
2.
2. Fifth root of 32 is 2. And what's the cube root of 27?
3.
3. Integer by integer. So rational number. Integer by integer. So rational number. What about G? Is it?
Rational. Number.
Yeah, because it is non-terminating, non-repeating. It's non-terminating because you can see the dots here. It's non-terminating and non-repeating because you don't find a pattern in the decimal part. It's 1011002103. You don't see a pattern there. So it's non-terminating, non-repeating, which makes it irrational. G is irrational. What about H?
Rational.
What is the value of fourth root of 1000, by the way? Cube root of 1000 is 10. But what's the fourth root of 1000? Thousand does not have a perfect fourth root. Cube root of 1000 is 10. Fourth root of 1000. No number, no natural number, or no number, okay, when multiplied by itself 4 times can produce 1000. Irrational. I, fourth root of 81. What's the value of fourth root of 81? Quick.
3.
3. 3 is 3 by 1. Integer by integer, rational number. What about J? Square root of 1681. Find out using the special division method.
41. 41.
41, correct. 41. So 41 is 41 by 1, integer by integer. So rational number. Rational number. Then K, pi. So we just understood that.
Irrational number.
Yeah,
Irrational number.
pi. Correct. Pi, the decimal expansion of pi is non-terminating, non-repeating. The value of pi or the decimal expansion of pi is non-terminating, non-repeating, which makes pi an irrational number. Pi is irrational because it has a non-terminating, non-repeating decimal expansion. That's the reason. So pi is irrational. 22 by 7?
Rational number.
Rational number. Because it has an integer by integer form. Very good. Okay, so that makes the introduction to this chapter. So in the next session, we shall learn how to find the P by Q form. Now, here you see 20.323232. You see the first one, right? So how do we put this in the P by Q form? How do you put 15.123 repeating in the P by Q form? So how do you write terminating decimals and non-terminating repeating decimals in their P by Q form? Is what and a little more is what we'll be seeing in the next class on Tuesday. I'll just stop the recording and I have a few questions to ask you.